Welcome everyone to NMC 113. I'm going to continue from where I left off in this particular chapter, but today we'll just be looking at the calculations that have to do with the stress and strain. We're also going to look at the elastic modulus, and then modulus of resilience, and also we'll also look at shear stress as well. And though it was not something that was discussed earlier, but I think that if we discuss it now in this session, it will suffice. So stress is actually calculated as you'll see like this formula in your notes. The average force applied, uniaxial force applied on the particular specimen over the initial area. This is how you calculate engineering stress. This is engineering stress. Later on, we'll also discuss true stress and true strain. But for engineering stress, we're assuming that the area remains constant, which is, according to that diagram, you can see it's not like really true that the area remains constant, because we know that it does change. So, but for engineering stress, this is for engineering purposes or experimental purposes. This is the standard formula that is being used. The initial or original cross-sectional area, which it will depend on the shape of the material. If it's cylindrical, you will have to use pi r squared. If it's square in shape or rectangular in shape, you would have to just multiply the width and the base to get the particular area. Now the units for this, it's megapascals, right? Units, it's megapascals. So if, say, the force is in newtons, right? Let's say you get the force in newtons and you also get the area in millimeters squared. Say you get the area in millimeters squared, square millimeters, and then you get the force in newtons. You have newtons per squared millimeters, right? And that actually equates to megapascals. But if your area is in meters squared and your force is in newtons, you're gonna have like pascals. The unit will actually be in pascals if the area is in meters squared and the force is in newtons. And then also you have strain, right? The strain is actually the change in the length over the original length of the specimen. So you're actually measuring how far the material has stretched, elastically, and also how much it, depending on how far you've actually pulled or applied the tensile stress in a uniaxial position, how far off you've stretched it, maybe into the plastic deformation zone. So this will be the length, final length, right, after you applied a particular stress, right? This will be the original length of the specimen, and then that will be the original length. So this change actually gives you the strain. It may be represented in this way as a fraction, or it may be represented in terms of percentages. That only depends on how it's given. So I mean, this is basically, I mean, it's in your notes. So say now you have we should have a pop-up here from the internet. I think I must disconnect my internet. Sorry about this, guys. So basically you would actually have something like this. This is, say, if this is your original sample, right, and you apply a specific force, tensile force in a uniaxial direction. In this case, if it's flat like that, it's actually in the horizontal uniaxial direction, and then it has an original length here, right, L0, and then after some time, when you've stretched it or you've pulled it with a set force, well, obviously the cross-sectional area here, it's gonna reduce. You know, it doesn't look like that here, but actually that's what happens. And then after you've done that, you have a final final length after you've applied the tensile stress or force. So what we also have is a constant, that's an elastic constant, right? An elastic constant. Let me just write it this side. Elastic constant. Now what you probably realize is the word elastic there. That actually means that it happens in the elastic zone. So the zone just before, just on the yield point, that's the elastic zone. Okay, this one is not particularly straight, but usually I don't know, wherever I took this this particular sketch was actually adapted from the internet somewhere. This is a very straight line. This is a straight line here. It's a constant. The slope is constant mostly, so you'd actually have something, let me just draw it at the top, something like this, right? This would be your strain, this would be your stress, and then for the elastic region you'd have a constant slope, right, until it gets to the yield point. And then you have a sharp turn there, and continue. So this particular slope, this is what I'm looking at, but here it's not particularly flat, but I think maybe it was an experimental one, so that's why they use this this solid black line. This is for what is called a 0.2 offset. This is a 0.2 offset, but we'll actually discuss this when we talk about the tensile test. So you have an elastic constant called elastic modulus, right, or Young's modulus, or modulus of elasticity. So it has many names, so let me just call it Young's modulus. And then this is okay, simple E. It's actually the change in stress over the change in the strain, but within the elastic region. That's very important, because it's actually this constant slope that I was actually talking about. That's the Young's modulus. So the constant slope from within the elastic region, it's actually called Young's modulus, and that's how it's calculated. And then you also have Poisson. I think it's probably French, Poisson's ratio. Otherwise, if you call it English, it's like Poisson's ratio. So yeah, you can call it whatever, Poisson's ratio. right? This is actually this is a sort of the lateral strain over the longitudinal strain, right? When you actually apply a tensile force on a specimen, what usually happens is that, let's say this is the original, and then this is the original, and you start applying, right, the tensile stress. You find that the specimen becomes thinner and becomes longer, right? But the area remains the same. I mean, not the area, the volume, because even though the, let me say the length here, let's say it's L2, right, and this was L1, so L2 is greater than L1 because you stressed it. And then let's say you have a cross-sectional area here, right? If you look from the top here, you have a cross-sectional area, and then also you have a cross-sectional area here. Let's call that A1. So A original is greater than A1. So actually you can see that with the area, the cross-sectional area becomes smaller when you actually apply a tensile stress. So that's when we're talking about when talking about the lateral change. Do you see that? So you actually calculate the change in the lateral length. Let's just say that from here to there, and then here to here. So you see the change. Originally you have this length here, and then afterwards you have this length here. So there's a if we look at it in terms of the axis, we'll say, well, there's a stretch x-axis, y-axis. This is just for argument's sake. When you're pulling it, assuming that the samples are vertical like this, you have the length actually increasing on the y-axis, which is the longitudinal change in length, and then it becomes narrower on the lateral axis, which is the x-axis in this case. So this is Poisson's ratio, and it's usually, the value for metals is usually 0.3, right? There's another another factor actually that I was supposed to discuss here, which is the shear stress. Shear stress and strain. And the shear stress, let me draw a particular specimen here, right? Okay, maybe I should draw it in 3D, something like this. Okay, so you have something like that, and a force is being applied. You find that let me just, okay, yes, it's a bit slanted, like it becomes a bit slanted like this. Okay, my drawing is not perfect, but you can see that there's a displacement here on this x-axis. So you can call that well, you can say this is A, right? And then because the force is being applied on all planes, on all sides, it's applying force here, applying the force here, and then underneath there's a force going upwards, there's also a force, and so you have this thing actually stretching and creating an angle, and then also stretching longitudinally. So the length that is actually stretches, we may call it h, right? So you actually have a formula for shear strain. Shear strain, okay, which is A over H, and that's basically tan theta, right? And the shear stress is just the shear force over the original area, and the units are still the same, in this case. And there's a relationship between the shear stress and the shear modulus of elasticity. So shear modulus of elasticity is just like the Young's modulus, right? Elasticity GM equals to shear stress over the elastic strain within the elastic region. So that's actually what it is. Also a change in those, and you can relate the shear modulus of elasticity with Young's modulus according to this formula, and also relates to the Poisson's ratio. So these are just formulas. I think we'll later on we'll go through some examples. And one more thing on the graph, right? You have to also, there's an area here. This area, you see the area underneath the elastic region, this entire area underneath the elastic region, right? That area is known as let me just do this, modulus of resilience. It's actually the amount of energy a material is able to absorb, right, before it actually starts failing, or starts deforming, not failing, starts deforming plastically, right? And it's measured in this is right, modulus of resilience, and it's measured in, here the units, it's not from his units, as joules per cubic meters. So it's the amount of energy that a material is able to absorb per unit volume, right, before it starts to deform plastically. And obviously, I mean, if you determine that area mathematically, looking at the other components, I can see this is a bit, too clouded, but I hope you can see what's happening. You have this half, your base is the elastic strain, and then you have the elastic stress. So that's basically it. And you can also have the formula if you relate it to Young's modulus, right? You'd actually have this. All this it's available in your notes, so don't trouble yourselves. I think the most important thing when it comes to this is understanding, so that when you deal with the questions, you will actually be able to use your understanding to actually formulate a proper solution. because what usually happens is that you'll be provided with a lot of information, and your understanding will help you to extract the necessary information to answer the question. So yeah, well, I think I'll create a secondary video again, or a third video, to deal with the tensile test, as well as discussing the difference between engineering stress strain and true stress strain, and relating the two. And also, if I don't finish those in a singular video, or the entire chapter, the remaining parts of the chapter in a singular video, I'll do a video, and I'll also cover the hardness tests, right? But it will be a very brief discussion, because most of the things are theory that you can read. So yeah, until next time, guys.